Or let me remind you where we left off. And that was here. Okay. Okay, I still haven't figured out how to move this. Hold on one sec. One sec. I'm gonna try to do one thing. Okay. Okay. I have to share screen now. Share screen. And here. Okay. So first of all, any questions from last time? Okay. Then let's pick up, and once again, if you have a question, you can either unmic yourself or you can raise your hand. And that's much better. Okay. Or you can write in the chat box, and that will be monitored, I hope. So we were talking about the Shapley value, and the Shapley value, you'll recall, it awards each player a weighted average of its marginal contributions to all of the coalitions of which it's a member. Okay, so this is when agent I joins the coalition S, this is the surplus it generates, this is its marginal contribution, and according to the Shapley value, agent I will receive a weighted average, so these are the weights of its marginal contributions to all of the coalitions of which it's a member. And at the end of last time, I was suggesting that I assume that I'm not quite sure how this works. How do I get it off of this? Yeah, I assume that I'm unmiked. Yes, I'm talking. Okay, so Okay. So at the end of last time, I was suggesting that it's very hard to look at a formula and say, oh, yeah, this is a good way of dividing the pie. This is a good way of solving the game. Or based on the player's outside options, this is a good way of assigning payoffs. And so I had begun to discuss the idea of listing out properties that we think a good solution, a good value should satisfy. These are reasonable properties according to which, or of any solution, of any method of apportioning the pie. So we had gone through these quickly. I'd like to go through them once again. So here is a list of 4 properties that may or may not be considered desirable properties, and they seem rather intuitive, of a value, that is, a solution to a cooperative game. And the first property is that we do divide the entire pie. We do divide the event. So this is an arbitrary value psi, and we're writing these out as sort of generic properties, not necessarily referring to any particular solution or any particular value, but for any value, these would be desirable properties, and that's why we use the notation, a sort of general notation for a value. So one desirable property is that it does apportion the whole pie, or we refer to this as Pareto optimality or efficiency, that nothing is left over, and it's also a feasible division. Okay? The next property is the null player axiom. And this says that if no one ever brings anything extra to the table, then they should just take what they started with or what they can get on their own. So you recall the definitions, a couple of definitions from last time. Player is a null player if its marginal contribution to any coalition of which it's a member is just its individual worth. So it never adds anything extra or special. So I'm not quite sure how to do this. Okay. Let's think about that. Whatever. So this is the null player axiom, that if no one ever generates any surplus, then they should just take what they can receive on their own. Anonymity says that if two players are substitutes, and you recall the definition of substitute, this says players I and J are substitutes if their marginal contribution to any coalition is exactly the same. So we take any coalition S, of which neither is a member, and if I were to join that coalition, or if J were to join that coalition, they would generate exactly the same surplus. So from the point of view of the other members of S, they wouldn't care at all whether I joined or J joined, because they're essentially equivalent. They're substitutes. And the anonymity axiom says that if two players are substitutes, they always contribute exactly the same to any coalition that they join, then they should receive the same reward. Okay? Additivity says, I had suggested this interpretation last time, that if you have two games, we define the sum of the games as the coalition-wise sum of their worths in the separate games. And one interpretation of this, I think I mentioned this last time, one interpretation of this is that, well, let's suppose we have two games that are played sequentially, right? So game V is played and we solve that, and game W is played and we solve that. Then the sum of the games would be the sort of the composition of the two. So let's suppose that instead we played them both simultaneously, or we conjoined them into a single game, so to speak. Then it shouldn't matter whether and then we solve that game. Then the additivity axiom says it shouldn't matter whether we solve them together or separately, that the solution to the sum of the games should be the sum of the solutions to the separate games. Okay? So whether you play these two games simultaneously and take your prize, your reward, your payoff, or if you play them sequentially and get a payoff in each in sequence, then you should get the same thing. You should go home with the same aggregate amount at the end of the day. Okay? And it turns out that, so I mean, the initial question is, are there any solutions? Can we find a solution that has these nice properties? And so the initial question is, does there exist any solution that satisfies Pareto optimality, null player, anonymity, and additivity? Well, indeed there is. The Shapley value satisfies those four. Moreover, and I refer to this as an axiomatic characterization. Moreover, it turns out this is the only solution that satisfies those four properties. So if we like those four properties, not only can we use the solution, but we have no choice but to use the solution, because every other possible solution, every other value will violate at least one of these. This is the only way to solve the game if we think that these are attractive features of a solution. Okay? So I'm not going to go through a formal proof of that, but what I'd like to do is just sort of suggest or demonstrate that the Shapley value does indeed have these nice properties. And so let's look at this sort of generic or typical three-player game. Okay, this is the sort of general procedure we use for a three-player game. I know this isn't true for all sized games. So as I mentioned last time, it gets very complicated to write out this algorithm for more than 4 players. But this is actually, it's true, you can get the idea by looking at just a 3-player game that this would hold in general. So let's first look at the axiom of Pareto optimality. Okay? And so Pareto optimality, in this case, or to demonstrate that the Shapley value satisfies Pareto optimality, in this case, this is the award to player one, this is the award to player two, and this is the payoff for the award to player three. And the claim is that if we add up those three, we get the event. Okay? So let me try to suggest the following. So what we're doing here is in order to determine player one's Shapley value, we're adding up these marginal contributions and we're taking the average. We're adding up these 6 entries and we're taking the average. And for player 2, we're adding up these 6 entries and we're taking the average. And for player 3, we're adding up these 6 entries and we're taking the average. Okay? So we're adding down the columns and we're computing the average. And then the question of whether or not the Shapley value satisfies Pareto optimality is then the question, if we add these 3 averages, do we get the event? Okay. Now I want to look at this somewhat differently. And I want to look at, instead of taking the average of, or the sum of the averages, I want to look at the average of the sums. So we're taking these sums down the column and taking the average. What if we were to take the sums across the row? It's the same. These, by the way, are the same 18 entries, whether we look at them horizontally or look at them vertically. But let's look at any particular row, okay? And take the sum across the row. What is that? Well, if we look at the first row, we have v of 1 plus v of